Yes. How's everybody doing tonight? How are we doing on the microphone volume? Okay, super. Well, welcome everybody. I've had a relatively long romance with artificial intelligence. It started about 20 years ago. I was an undergraduate, and I was working on something called Cas5. So we were using neural networks to predict the secondary structure of proteins. And it was kind of like a game to me, and I became really curious as to how you could shave incrementally more performance in training these models to predict something that was actually a very natural and organic process. And I was hooked from that moment. And 17 years later now, a lot of the things that we held to be theoretically true and were in fact provably true and are true to this day turned out in practice to be really, really wrong. And I'll give you a very simple example of that. How many people have heard of deep neural networks? Okay, great. So we were taught, and there's a theoretical result that says you only need 2 layers to a neural network. It's plenty expressive at just 2 layers. There's absolutely no reason to deepen a neural network. And here we are, 2017, that turns out to be completely false. And so I want to talk today about the big picture of artificial intelligence, narrow artificial intelligence, general artificial intelligence, superintelligence, and I have a little section for practitioners on the end to talk about in practice, when you actually use machine learning, when you use artificial intelligence, what are some of the difficult problems and how do you overcome them? A quick question, I want to understand the technical level of the audience. How many people are developers of some kind? Okay, great. And then, so on the other side of the house, we have people who are just getting into data science, learning something new. Okay, great. And then how many of you would classify yourselves as business people? Okay, good. So I think that we roughly can segment the audience into about 3 sections. And there should be something in this talk for everybody. I'm not here to talk for my benefit, so I hope this will be very interactive. And this universal symbol for confusion or you can't hear me, it was just something like this, right? So if we're going too fast at some point or too slow at some point, just kind of raise your hand or give me a quizzical look. Oh, we've already got a hand. Yeah, what can we do about that? Oh, you want to try, let me turn off amplification and see what we get. Thanks, Orion, by the way. See, it's good when people actually speak up, it makes a difference. Okay, so this is no amplification. Is it, yay, okay, well, I can lose the microphone. This one kind of looked silly anyway. Okay, great, so give me just 1 second. So that's a great example of somebody doing something which feels difficult, but it ends up in a better result for everybody. So I hope you'll do that throughout the talk. Not necessarily when I'm mid-sentence, but I'm really here for your benefit. And I want to share with you what I've learned over the last 15 or 20 years. And I want to get you ready for an aspect of computing that is going to touch every single aspect of everyone's lives. So we all saw the advent of the cell phone. We saw the advent of the computer. And artificial intelligence will be as ubiquitous as all of those things. Wherever there's a computer, you're going to have AI. So let's jump into it. So the definition of AI is actually extraordinarily simple, and it's machines acting like human beings. However, because it's a technical discipline, we have to be precise. And there's actually a lot, terminology soup. And one of the most common questions I get asked is, what is the relationship between AI, machine learning, and deep learning? Well, this Venn diagram is actually designed to answer that question. So AI is really the umbrella discipline, and it encompasses a lot of different things. And over time, especially in popular culture, the definition of AI has moved. So I want to stick with the simple definition that we started with. It's that AI is machines acting like human beings. And I want to say that machine learning is a sub-discipline of that, and then deep learning is a particular set of algorithms that work inside of machine learning. Classical AI is divided into 4 different areas, and those are search, planning, optimization, and learning. Some quick comments about each one of them. I've bolded search because if you can understand how artificial intelligence works in search, you're going to understand AI across the board. And if you squint hard enough, or from a mathematical perspective, if you look at each one of these at a high enough level of abstraction, they're all the same thing, right? So search is you have a graph, you have a space, and you're looking for a particular state. You're looking for something specific in that graph. I'm looking for the gold coin. Planning is the idea that, hey, I have some goal that I want to achieve. I have a set of operators that I can use to apply to the world. How do I string all of those together into a coherent plan that gets me where I'm going? Optimization is I have something which we call, you don't have to remember all these terms. I'm just giving you, getting in the groove here. So optimization is the idea that you have an objective function and you want to optimize that in such a way that you get the maximal output. So you're trying to maximize the result. A really simple example is like game playing. right? So in chess or in Go, and we're going to talk about both of those games today, we want to maximize the objective evaluation of a given position to get to a winning result. And then there's learning, which is machine learning. And this is the idea that we have a labeled corpus of examples, and we show those to a machine, and it develops a generalized hypothesis. This little pink or purple dot in the upper left there is the singularity. And it's outside of the main Venn diagram because I don't want to talk about it. I don't think it's a very scientific term. It's a word that's bandied about a lot. I think it gets glommed in with a lot of science fiction and science fantasy. People have the same criticism of superintelligence. We are going to talk about superintelligence today. But singularity, I'm happy to take questions about that. I just don't think it's a very meaningful topic to talk about. It's more a philosophical topic. There's nothing wrong with it per se. The best criticism I've read of it, it's like talking about the singularity is like saying, well, let me assume that all hummingbirds speak French, and now I'm going to tell you how a United Nations of hummingbirds would work, right? You're starting with this really, really gross assumption. It's a giant leap. So this is the big picture of what AI is from a discipline standpoint. Any questions or comments so far? OK, great. Let's keep moving along. So we started with this simple definition, and the one thing that I want to establish in this talk and that I want to demolish permanently is the idea that machines are mathematical or crystalline or objective. So what we're going to prove in this talk, and we're going to show it in lots of different ways, is that machines are never objective. Artificial intelligence and human intelligence as a whole always relies on bias, always relies on shortcuts, and it always misses something, and there's no way around this. So we're going to start with a technique that Google developed called inceptionism. And are people able to actually make out what's on the right here? Yeah, it's a pile of bananas, right? So the idea behind inceptionism is really simple. And it says that we're going to start with a model of some kind, and we're going to feed that unbiased information. And that model then is actually going to emit some view of what its concept of the world is. And I'm going to show you some very concrete examples here in a second. So what we're looking at here, these are all image recognition deep neural networks that Google trained. I think these are all convolutional neural networks. And they're designed to recognize specific things. OK, so I don't need to read for you. Upper left, you have the hartebeest, measuring cups, ants, starfish. Lower right, the screw. And so this is really fascinating. And the basic idea behind inceptionism is that algorithms which are trained to recognize something also have a lot of the information that's needed to actually generate that something. It's a fascinating idea, right? So how many people have heard the term Platonic ideal? Okay, so the idea is that, so what Plato said is that we've got all these different forms in the world. You've got dogs, you've got cats, you've got human beings. However, with a very small number of examples, anybody is able to infer, like you can show, once you teach a 2-year-old what a dog is, doggy, doggy, doggy. They're going to be able to generalize to see what all those dogs are. So what we're actually looking at here with inceptionism is we're kind of looking into the Platonic ideal, or the machine's template, and the machine's view of what that concept actually looks like in its truest form. Okay? And the interesting thing with inceptionism is, again, that we're starting with essentially no information. We're starting with unbiased information. You feed it through the neural network. You can do this with any classifier, and you ask it, what do you see? What do you see? Do you see anything? Are you sure you don't see anything? And eventually, you get these really fascinating hallucinations. We're going to talk more about that in a second. So this is an image recognition classifier, also a deep neural network. What was it trained to recognize? It was trained to recognize dumbbells. And the first fascinating thing we're going to see here is that machines can be confused the same way that people can be confused. And so the co-occurrence of these two terms, so in the training corpus, when it was trained on thousands of images from gyms around the world, I don't know, the co-occurrence of arms and dumbbells was so high that this machine really isn't able to cleanly distinguish between those two things. And I think on the prior slide, no, it's coming, oh yes, on the prior slide, look in the lower left, you see the anemone fish or the clownfish. It's the same thing. Like, what is the actual difference between a clownfish and an anemone? It's really hard to tell. And this is an example of a machine showing some level of confusion. And the important thing here is that if you were to show this classifier an arm, somebody's arm, you would get what we call a false positive out. So that's something the machine is going to say, well, this is a dumbbell, but no, it's actually not. What you've been able to do is actually confuse that machine or trick that machine by virtue of the concept that it's learned. So here is another one. I don't know how many, I mean, these are startlingly beautiful, and I hope you'll find the time to Google Deep Dream and take a look at some of these images because they're beautiful. I've got a couple more. I could look at them all day. How many people remember, can you see some of the detail that's in here? Back there, okay. How many people remember as kids looking up at the sky and you're looking at clouds like, oh, that's a turtle, that's a horse, that's a dog, that's a car. Do you guys remember that? So this is the fascinating thing is that machines have enough intelligence and enough structural perception for us to do the same thing with them. And this is the whole idea behind deceptionism is we're going to feed it an unbiased image, just a natural image of a sky, and we're going to keep asking it to emphasize the things that it thinks that it sees. And eventually what we get is this Platonic ideal where we see a projection of the machine's concept in the real world. It's not as easy to do inceptionism with all types of algorithms. These happen to be visual algorithms, so it's very easy to see actually how the machine is working. It's a lot harder with other types of AI. But the important thing here is that you're starting with unbiased information. You're coaxing it. You're repeatedly feeding that to that classification algorithm. And then you're getting out something like its Platonic ideal or its biases. This is going to be really important in just a second. More examples here. I mean, and these are amazing. And I don't know if you can see on the bottom, Google gave these some neat names. The camel bird, the dogfish, the pig snail. These are grade A hallucinations. They're beautiful. And the thing is they have a natural logic to them, which we're going to talk more about in a second, right? And here again, we see unbiased images top. We apply inceptionism, and the machine is like, well, you know, if you keep asking me, I guess I'm going to tell you that that pile of leaves is actually a bird. And I guess I'm going to tell you that that tree is actually a pagoda or whatever that is, and that mountain is actually a building or another pagoda there. And this is something that is a general pattern of intelligent systems as a whole, and it's called the law of the instrument. So Abraham Maslow, there's a lot of overlap between philosophy and artificial intelligence because it's actually really difficult to define what intelligence actually is. So all the philosophy that I'm throwing at you is just to make things clear. Yes?
So I'm just trying to summarize what you said so far.
Sure.
So you're saying that machines have limitations, and one of the limitations is that they can't recognize things that humans can? How does inception?
Right. So, well, actually, the idea behind inceptionism is simpler than that. And I don't exactly mean exactly what you just said as a summary. But what I mean to say behind inceptionism is that we can peer into the bias that machines have. That's the short of it, right? So we can get an outside glimpse. As an outsider, we can look as to what types of concepts the machines are forming. And these concepts can have the same kinds of pathologies that people have, confusion, hallucination, right? It's hard to even call those pathologies. But basically, machine perception has some of the features of human perception, and that includes all the flaws. Make sense? OK, great. So Maslow's idea is that if all you have is a hammer, you tend to regard everything as a nail, right? And so this is this predisposition, right? And you can see this operating in human beings. This is called pareidolia or apophenia. On the far left there, you see the face on Mars. Right? And then we have this general phenomenon, like which you'll see on the National Enquirer or maybe at your neighbor's house, that, oh, I see Jesus in a piece of toast. Right? And so what is happening there is that we have a brain and we have a pattern recognition system that is just really, really, really good at detecting faces. And because it's so good at detecting faces, it's also really good at seeing faces where they're not there. Right? So we saw an example of confusion. This is an example of confabulation or hallucination. And what I'm trying to establish here is that both people and machines aren't fully objective in their perceptions. And I guess it's odd now that we've seen machines that can be confused and hallucinated. And we're going to put this on more firm ground. But this is really the intuition for the fact that all machines and all classification algorithms have a fundamental bias. We're going to look at this much, much more deeply as we go on. Any questions or comments so far? OK. Moving right along. So now we get to the theoretical part of the discussion. And what I mean to say is that not only is it the case that the AIs that we've trained to date are not objective, but it is baked into the pie. It is a mathematical fact. It is gravity for artificial intelligence that you cannot have an intelligent system which is free from bias. So you will never have objectivity from an AI. And then lots of people will come up and apologize. And they'll say, oh, you need better training data. You need better algorithms. Nonsense. It's baked into the pie, and it's a fundamental law. You can't defy it any more than you can defy gravity. And we're going to talk about why in just a second. So if you only take away one thing from this talk, remember this diagram, OK? And the idea here is that at the root, so at the very, very top of that diagram, we have the initial state of the world, so to speak, right? And we said earlier that we were going to phrase AI as a search problem. And the idea is that the edges in this graph, so the nodes are those circles, the edges in this graph represent different situations or contingencies that the AI can encounter or actions that the AI can take. And what you'll see is that it has this tremendous branching structure here. And for those of you who are mathematically inclined, the number of states grows exponentially. So this tree gets really huge, really, really, really fast. Okay? And we can think of AI as a search through enormous spaces. And our definition of enormous is very simple, and it's simply that a brute force search, or looking under every rock and every leaf, is impossible. There are way, way, way too many states, more states than the number of particles in the universe. And the idea is that we talked earlier about an objective function. How many people are familiar with the term heuristic? How would you define a heuristic?
Rule of thumb.
Yeah, thank you. Excellent. It's a rule of thumb, right? So in order for the AI to cut through this enormous space, it has to start making guesses about where it thinks the gold is, so to speak, or where the goal, G-O-A-L, is actually hiding. And what you'll see here is that this kind of yellowish path is the heuristic, right? So this is what allows the AI to prune an enormous search space down into a smaller, more tractable or manageable space, and hopefully to find one of these goal states. Okay? And the goal state is what you are looking for in search, what you are trying to plan for in planning, and so forth, right? What you're trying to optimize for in optimization. Now, I want you to notice very deliberately here that there are goal states which our heuristic didn't find. And then that's going to become significant as we move on. So I want to give you some appreciation for the enormity of these search trees. And chess is a really simple example. We're going to talk about some even more complex games like poker and like Go as time goes on. But this is what we call a combinatorial explosion. So when you start a game of chess for the very first move, I think this includes both black and white, there are only 400 possibilities. OK, seems normal. And very quickly, after 4 moves, you're at 288 billion possibilities, right? And when you actually follow this to its logical conclusion, you have something like 10 to the 40th legal positions in chess. This is an astronomically sized number. And you have 10 to the 120th possible chess games. These are huge numbers. And to give you a sense for how big those numbers are, there are roughly 10 to the 80th particles in the universe. Okay? So there are more, famously, there are more possible chess games than there are particles in the universe. The important thing here is that you simply, using brute force search, even if you could write one chess game on every single electron, would never be able to go through all chess games. And yet, the beauty of AI is that using good heuristics, we can still have a chess-playing computer that can trounce any human being on this planet. We'll talk more about this as we go on. But this, again, is combinatorial explosion. And what I want to give you a sense for is how quickly this state tree actually explodes. All right. So AI can be thought of as a search through enormous spaces. They're enormous because we can't brute force them, right? And brute force just means literally we're going to try every possibility. Not possible. Won't finish in my lifetime. Won't finish in yours. So what we're going to show now on some more theoretical angles is why you will always have an AI that relies on shortcuts. So you can't say, well, first of all, from a sheer size standpoint, all of the domains that are interesting, image recognition, game playing, self-driving cars, you name it, financial optimization, the search spaces are huge, just like the chess search space that we just described. And I want to give you some theoretical foundations for why a heuristic or why a form of bias will always be required. And so you can prove this mathematically, and I won't bore you with that in this talk, but you can actually show that if you were to create an artificial intelligence algorithm with no bias, it would only be able to do one thing, and that is memorize everything that it has seen before. It has no capacity to generalize about the future. What is bias? So bias is something, it's kind of like this heuristic. It's this rule of thumb that the machine uses to cut through, to shrink that search space in the world. But this something is something that cannot be proven. So is anybody familiar with the problem of induction? Okay, so basically David Hume, philosopher, he basically said, look, it's great. We have science, we have math, we have philosophy, but they all rely on something that cannot be proven. And that something is that the future will resemble the past. So this fundamental problem of inductive bias is that in order to do or to perform tasks in what we would call an intelligent way, the machine has to make gross assumptions which are not warranted. And this is the idea behind inductive bias. Does that make sense? Because if it doesn't make sense, it's going to be hard going forward. Make sense? OK, great. So now, here's the crazy thing. It turns out that this is also true for human beings. How do we know this? Well, there's a neuroscientist by the name of Antonio Damasio, and he studied people with selective brain injuries. And long story short, what he found was that people who lose their emotional capacity also entirely lose their capacity to act rationally. So you can have people whose memory is intact, whose concrete operations are intact, whose ability to do math is intact, but because the emotional parts of their brain are damaged or removed, they cannot function the way a normal human being can function, right? And he called this book Descartes' error because if you, everybody remember has heard like, I think, therefore I am? Okay, so it turns out that Descartes was wrong, and what he should have said was, I feel, therefore I think. And what emotion is really doing for us, it's getting us around analysis paralysis. So does everybody remember Vulcans from Star Trek? Okay, great. So this is hyper-rational race. Well, the fact of the matter is that Vulcans would never be able to get out of bed in the morning. Because without that emotional bias, you're going to be thinking about like, oh my God, you know, what if my kid gets bitten by a wasp today? What if a meteor strikes the Earth? I mean, there's just a limitless number of possibilities and scenarios that you have to run in your head. But the thing that gets you out of bed is, I gotta eat. Right? So that's this biasing function, like, I got to eat, like, my wife has just, you know, kicked me in the head, like, it's time to go to work, right? I have to work, whatever that is. And so it serves the same function in human life. And what I want to point out here is that what we call emotion is just actually a form of biasing. And again, the universe, the world that we live in is immensely complex. The only way we can get through it is with some sort of biasing function. And that biasing function is emotion. Questions or comments? All right, so why does this matter, right? So who cares? Algorithms are biased. Well, algorithms rule the world, right? So when you do a Google search, what controls what you see? What's that? I can't hear it. Yeah, the content ranking algorithms, right? When you're on Facebook, and it's something like the average adult in America is now spending like 60 minutes or 50 minutes a day on Facebook, right? What controls what you see? The content ranking algorithms. And so the point is here is that an enormous billions and billions of dollars in the fiscal economy and billions of human hours in the attention economy all go to paying attention to things that algorithms think are important. And those algorithms are not objective. So the first interesting question becomes, is the algorithm showing me anything that it thinks is important that is not actually important? And is there something that's important that it's not showing me? And those are what we call false positives and false negatives, respectively. The other thing which is interesting to think about is that the great companies of our time, Facebook, Google, I'm sure I'm forgetting somebody in here, are advertising companies, right? And we are moving into an age, so how many people have heard this term Turing test? Okay, what is a Turing test? Great, great. So the Turing test is, can a machine pose as a human being and trick a panel of vectors? Well, there's a new concept coined by my friend Balaji Srinivasan, which is Turing authentication. Are you this specific person? Right? And this is exactly what Google wants to do. They want to Turing authenticate you everywhere you go, because once they know you, they'll be like, oh, it's Adam. Adam likes Ferraris. Adam likes soccer. And once they know that, it's checkmate. Right? And what the advertisers who flock to Google and flock to Facebook are doing is they're selling into your bias. Right? So we have a set of algorithms which are themselves biased and which are trained by our personal biases to sell us, again, our own biases. It's a very, very complicated series. And that's why we need to start thinking of machines as a mirror for our own behavior. And we saw earlier that machines can have obsessions. Right? So like a machine that is trained to recognize fish, you're going to show it a sky, and it's just going to see fish all over the place. Does anybody remember the Lego movie? Okay. Do you remember the spaceship guy? Like, and he's waiting the whole movie to make a spaceship, and then finally he gets to make a spaceship, and he's ecstatic, right? So that's true for all of us, right? We all have a set of keywords. Our minds are very, very hackable. And the first important thing that I want you to get to think about is, like, what are your personal keywords? Those are your biases, and those are the things that cause you to look right instead of looking left when you're walking through the world. Those are the things that you think are important, and they may differ from the things that other people think are important. So the first, I think, beautiful result is essentially that because so much of our behavior and our attention economy is studied by algorithms, we can use inceptionism to peer into those algorithms and reverse engineer what our own biases are. It's a fascinating way to know ourselves. And it will also help us to know what Google is getting wrong and what Facebook is getting wrong. That's really important given how much money and how much time is going into those sources.
Could you say that again? Reverse engineer by being able to see what the algorithms have profiled us to be?
Wow.
Visualizing what the algorithms have learned?
Yes, I think. Okay, so here's the simplest way to say it. So in order to run an effective advertising platform, the Googles and Facebooks of the world need to study our behavior, right? So as they study our behavior, they build models of things that they think we're interested in. And those models are a way of knowing ourselves. That's it, right?
And those models are what?
They're ways of knowing ourselves, right?
Is there a way to, are you saying there's a way to get them to project that into
Yes. Yes, I am. And that's what inceptionism is all about. It says, hey, model, cough up your bias.
So it's not a black box. You're saying it can be made into depicting it as a picture?
Sorry, yes. This is just pretty. It's never this easy, by the way. It's only this easy for image recognition algorithms. I just put this up there because it's amazing. I can look at it all day. But yes, so you're exactly on the right point, which is that inceptionism is a way of peering into an algorithm. And inceptionism is extraordinarily difficult for non-image-based algorithms. I am not trying to trivialize this problem. It's really, really hard. Okay? But to give you a simple example here, I guarantee you that if you went to Facebook, they could rank from 0 to 500 who the most important people in your life are. Guaranteed. 100% guaranteed. Now, is that ranking correct? Who knows? Does it affect what you see? Uh-huh. That's the big point. Did that answer your question?
Yeah.
Okay, great. I know this is all.
Vision algorithms could allow peering into the algorithms that are black boxes.
Right.
You're saying the direction you're going.
So inceptionism is easier with vision algorithms because you get a picture, right? But you can do it, and we need to generalize this process, and we need to work it on all kinds of algorithms, right? Like I guarantee you that Facebook knows things about you that you don't know about yourself. That's another way of saying that, the same thing. All right, so let's look at the big picture here. So we're going to start, the hierarchy here is narrow intelligence, general artificial intelligence, and then superintelligence. I meant narrow artificial intelligence, right? And narrow artificial intelligence is where we are today. If we're able to build a machine that passes the Turing test, we have general artificial intelligence, which is a machine that can act in all capacities like a human being. And then if we reach something called the takeoff point, we will have superintelligence, which is a machine that is far superior in its intelligence to any human being on this planet. Let's talk about narrow AI first. So we are at superhuman narrow AI today. We're living in this time. Medical imaging, face recognition, drug discovery, fraud detection, poker, and Go. There isn't a human being on this planet that can do these things better than machines. And I want to look at poker and Go because I think they're kind of really interesting ways to understand at a high level what the progress in the fields of AI are. But the important thing here, the idea behind narrow AI is like, look, we're not going to be able to, well, at least under narrow artificial intelligence, it can't do everything, but it can do one thing really, really, really well. We'll talk about the drawbacks of that in a second. So what's the deal with poker? Carnegie Mellon just finished this system, and in February, it played, I want to say it was like a 2-week match with 4 poker pros. And these guys wanted to go home and cry at the end of the 2 weeks because this machine was absolutely invincible. And what's interesting about the game of poker is that this is a very touchy-feely game. It's a game theoretic environment where the machine has to bluff. You're dealing with uncertainty. You're dealing with collusion amongst opponents, competition. And the fascinating thing about this is that the machine is not only able to bluff, but employ deception as part of its strategy. Another feature of modern AI systems we're going to see is this concept of self-improvement. And in the case of Libratis, it played more than 1 trillion hands of poker against itself. It used something called counterfactual regret minimization, which is essentially a Monte Carlo simulation, which allows it to look out into the future and pick the path that's least likely to lead to failure. You don't have to remember the name of the algorithm, but the important thing is it's a self-improving machine. And we're going to look at AlphaGo in just a second. We're going to see the same pattern, that the machine gets better by playing itself. It only gets marginal improvement in the beginning from human games, and then it takes off in its ability when it starts to train against itself. The neat thing about Libratis is that it was built from 3 different systems. So the first system I just talked to you about, it's the regret minimization system. And it basically allows the machine to pick the lowest cost path into the least likely to fail path into the future. The second system was designed to focus the attention of the first system. Does anybody want to guess what the third system did and why? Right? What's the worst thing you can do in poker? Showing your cards. You can be predictable. So the job of the third system was to hide the tracks of the first 2 systems, right? And you can imagine the pain in playing against something that is this deceptive, this good at bluffing, and has so much historical data as to how hands work out, not to mention perfect statistical information. The important thing here is you have systems watching systems watching systems. And I think this is a fundamental property to how intelligence actually works, is self-referentialness or self-improvement. Let's talk about AlphaGo. So it was expected, when you actually look at the game of Go, it has 10 to the 100 times more positions than chess. It's a much, much more complicated game. The state space is a lot larger. And it was expected it would take another 10 years to crack Go, and it was cracked basically last year. I think they still have to defeat the world champion, but this machine is amazing. And the thing that's really fascinating about it is that you think of Go as a game of intuition and aesthetics. A Go master makes a move because it feels right. And here we now have a machine which has a really good gut check and is able to defeat people who have spent their entire lives, dedicated their entire lives to this game. We talked earlier about systems monitoring systems, and the idea behind AlphaGo was that as a deep neural network, you can build up concepts from simple to complex. That's the whole idea behind the depth of a neural network. You go from a simple concept all the way up to a complex one. So here again, we see this idea of abstraction. And again, self-improvement was critical. They first showed it 30 million master games. This is kind of interesting. And it got just better than a coin cost, 57%. And then they spent time just playing thousands of games against itself. So it used human games and human information to get a little bit better than random, and then it played itself until it was amazingly good. A lot of information. I know it's moving really fast. Are people still following me? Do I need to slow down? Is you getting it so far? OK, great. OK, so this is just to give you an appreciation. So again, it's 10 to the 100th times larger. This is the number of possible games or possible positions, actually. And so this number is actually 10 to the 140th power, right? Again, 10 to the 80th particles in the universe. Brute force isn't going to get you there. You need a heuristic of some kind. You've got to start taking guesses and shortcuts. All right, so that is narrow artificial intelligence. I want to talk about general artificial intelligence here. And we're not doing well here at all, right? So the thing about narrow artificial intelligence is that in a given domain, it'll give you superhuman performance, but it's really brittle, right? So I can take, like Lebradas, this brilliant poker playing algorithm. It can't play tic-tac-toe. I can take a chess computer that will beat anybody in the world. It can't play poker to save its life. So what we see is this tremendous brittleness, that AIs are really, really good in specific domains, but they're not good when you try to generalize them. The next thing, which I find pretty fascinating, is that the things that are easy for human beings are actually the hardest things for machines. So walking, talking, reproducing. Those are things that any human being can do. I mean, it requires a certain age in order to be at an age where you want to reproduce. But the easiest, most natural things to human beings are actually extraordinarily difficult for machines, right? And so the other thing we notice is this resource hungriness here. So remember, Lebradas played more than 1 trillion hands of poker against itself. So one of the things that we have working against this trend or this attempt to reach general artificial intelligence is that it's just going to take too much computing power. There's also a theoretical, I'm on conservation of performance here. There's also a theoretical limit, which is called the no free lunch theorems. And it basically says that any algorithm which does really, really well in one domain must suck at something else. Right? So it's the idea that performance kind of regresses to the mean. And you can kind of see this, right? Like, so if I have to compete in a computer programming contest with Bill Gates, I'm scared. But if I have to run a race against him, I'm happy, right? And so this is the idea, and we see this in human beings, that people tend to be good at a few things but not good at everything. The next part that I'd like to illustrate is how difficult it is to actually specify or instruct a machine to do really simple things. And the best example that I found, how many people have seen this video on YouTube? OK, great. So it's really funny. And I think it's called something like the exact instructions test. And this father, he has 2 kids, a boy and a girl. And he asked them, he's like, look, I want you to write exact instructions for me to make a peanut butter and jelly sandwich. This ends in tears and anger, by the way. So this is the father now following the son's instructions to put the peanut butter on top of the bread. What? He's putting the peanut butter on top of the bread. It's a very simple instruction. And the point is that a lot of things that we take for granted are actually very, very difficult to explain to a literal-minded agent, like a computer. Now, here again, so I don't know if you can see on the bottom, there's a piece of bread. The son said, put the jelly on the bread. And the dad is putting the jelly on the bread. So as this progresses, the son, eventually starts to hyperventilate. He has a nervous breakdown because he's trying so hard to please his dad and to explain how to make a peanut butter and jelly sandwich, but this, literal-minded dad can't get it. And his daughter wants to murder him during the course of the video, right? The important thing in all of this is that what we call value loading, explaining to an artificial intelligence what we actually mean, is really, really difficult. There are all kinds of conundrums, moral conundrums, that people can't solve, and we cannot, once we have self-driving cars, we cannot expect that machines will be any smarter than we've programmed them to be. A really good example is a self-driving car. What if it has to choose between the life of the passenger or the life of somebody outside the vehicle? What if a machine has to choose between a very low probability of killing a lot of people or a very high probability of killing a small number of people, right? Extraordinarily difficult. And we as human beings have not succeeded at value loading our society. I think this is politics. Politics and international relations is trying to get people to behave in ways that are mutually beneficial. Well, we as human beings haven't solved this. There's no indication that we're going to be able to load our value systems into computers, right? And does anybody remember the science fiction author Isaac Asimov? So this is what the 3 laws of robotics are all about. And those of you who have read the books know that there are problems. And the definition of human being, the definition of robot, is very fuzzy. And you can imagine there are all kinds of what are called perverse instantiations. So if we have an AI or a super AI and we give it a goal like make all human beings smile, does that mean paralyze everybody's facial muscles so they're permanently stuck smiling? There are all kinds of weird and perverse instantiations. And the peanut butter and jelly problem shows that it's hard enough to instruct a human being in a way that's actually meaningful. A couple more points here. And the one, I guess, thing that you should understand about how difficult it is to mimic human behavior is that there's a model organism called C. elegans, and it's a worm. It has about 300 neurons, and we have not succeeded at modeling that organism. There's so many complexities. We need to know the strength of each of the connections. We need to know whether they're excitatory or inhibitory. There is so much to model in even such a very, very simple organism that if you actually start to think about the amount of modeling power that you would need to model a human brain, really at a very, very deep level, we just don't have it. And even if Moore's law continues for another 100 years, we won't be able to do it, right? So we're going to need, these are the things that make AI difficult. So just doing the easy thing and saying, hey, well, here's a human level intelligence right here on your shoulders, let's simulate it, is not going to happen because it's computationally infeasible. The other thing that we look at is that on the very bottom here, machines need to be trained in order to be able to do what is called inference, actually make decisions in the real world. And if you look at a system like Libratus, I mean, playing 1 trillion hands of poker to be really good for 2 weeks, that's a very unfavorable ratio. And it is not clear that we will have AIs which are flexible enough or have enough return on investment of resources for us to actually be able to get them to general intelligence. There's actually, I could stay on this slide and keep talking for another hour, but I want to make, is everybody following this so far? Any questions or comments? OK, great. Let's go up the hierarchy. And a quick detour here. Then there's some pretty pictures to look at here. I want everybody to think of evolution as a form of computation. And what we have in evolution is an eons-long optimization problem. We're trying to build organisms that can survive. And we're running billions and trillions of experiments by the moment, and we do it over the course of billions of years. And we get things that look beautiful and that look organic. Does anybody recognize this? Yeah, almost. Yes, this is Romanesco broccoli. And nature has kind of this beautiful organic logic to it. And what I want to submit to you is that that is the result of a long process of computation. And where this becomes interesting is that in using generative design, there are all kinds of designs which people would never dream up in their wildest imaginations. But when you put a person and a computer together, this antenna design on the right is actually twice as efficient as the antenna design on the left. Some more startling examples here. So far left, that is the human design part. Far right, this is the generatively, artificially intelligently designed part. And here's the difference. Same strength, same performance characteristics, it's 75% lighter. stronger in some cases. And in a construction project, you can eliminate 40% of the material that you would need, but it's a design that a person in their right minds would never think about. And the thing that I think is really compelling is when you look at that, it looks like something that's natural. And here again, the idea is that evolution is actually a process of computation, and we're just simulating or brute forcing or condensing evolution with intelligent systems. This is an engine block. Again, massive weight savings, similar, if not superior strength characteristics. And this is what you get when you bring human beings and machines together. This is another a stem for a bicycle handle. Again, you see massive weight savings, equivalent strength. And a lot of these came from a project that Autodesk did called Dreamcatcher. You'll notice in brackets there I have an AD, I have a bibliography at the end. These are all just references. All right, so what is important here? So AI is artificial intelligence. There's also something called IA, which is intelligence amplification. And the idea here is that we can use computers and human beings in concert. That's really what Dreamcatcher does. It gives the designer new ideas which it would never try. And if you watch a computer do something really well, like when you watch a chess game and you see a computer move, it's a move that's obvious in retrospect, but nobody in their right mind would have thought to make. And so this is a really fascinating frontier, intelligence amplification, where people and machines are working side by side. You can think of it as human-in-the-loop computing or computer-in-the-loop humanity. All right, moving along. So let's talk briefly about superintelligence. How are we doing on time? Good, okay, super. So what is superintelligence? Well, everybody understands the concept of general artificial intelligence. And general artificial intelligence is an AI that is equivalent in its functionality or its functional capability to human beings. Superintelligence is the idea that a machine would be vastly superior to a human being. So I want you to take everything on this slide with a grain of salt, because it is not at all a given that we will be able to achieve superintelligence, or machines will be able to achieve superintelligence. One thing is the case, though, and that's that if it happens, if we haven't prepared for it beforehand, it can have disastrous consequences. In that sense, it's like the race for the atomic bomb, right? It wasn't really known if nuclear fusion was possible, but they locked a bunch of smart people in a room for 10 years. It happened, and it changed the world, in some ways for better and in some ways for worse. So the first property of superintelligence is this idea of punctuated equilibrium, right? So Stephen Jay Gould coined this term, and when you look at the fossil record, you look again at the past, which is just this long-running computation, you'll see that everything is kind of the same, kind of the same, kind of the same, and then boom, you have quick and sudden changes. And the history of humanity on this planet is really a study in quick and sudden changes. And this is a look at world GDP, which 10,000 years ago, when Homo sapiens became the dominant human species on this planet, was nothing, and now is this enormous number, right? And you see this throughout technology. It's that there's nothing, there's nothing, there's nothing. It's stable, it's at equilibrium, and then boom, there's this punctuation, there's a sudden event. So that's really the incentive to prepare for this moment, or the possibility of superintelligence, or even general artificial intelligence at that. So the important point here is that the crossover is the point at which the AI can train itself. Okay? And remember, looking at AlphaGo and looking at Libratus, we saw that these systems were introspective. They can look at their own play, they can look at the play of others, and they can improve themselves based on that. And the idea, so the speed of the takeoff, this is a very simple model from Nick Bostrom's book, I'll show it to you in the bibliography, is that the speed of the takeoff will be a function of how much optimization power we can throw at the machine. That's network, that's compute, that's storage, divided by the recalcitrance, right? So we saw earlier that, like, wow, 1 trillion hands of poker to become good. Is it a marvel? Yes. Is it a lot of training? Yes. Okay? And so the idea here is that if AI turns out to be very, very inflexible, we're rolling a stone uphill. We can throw tons and tons of optimization power at it, but the takeoff is not likely to happen. Now, if, on the other hand, optimization power continues to grow with Moore's law and recalcitrance is a relatively small number, we get takeoff quickly. Does that make sense? Yeah.
So, yeah, this is in Nick Bostrom's book. I still don't understand recalcitrance, though. Can you explain what recalcitrance is?
Yes, stubbornness. That's it, it's stubbornness, right? So think of this as a dog. The optimization power is how much energy, how many treats you can buy, how much time you can put into your dog. If your dog is fucking stubborn, it's over. That's it, that's recalcitrance. Okay. Right. Good question, good question. So we already saw earlier why value loading is difficult, right? So it's very hard to direct this AI. And then when we are dealing with something that has a 10,000 IQ that is smarter than any human being on this planet, it's not going to be possible to contain it. So this is the whole idea behind superintelligence, is that we need to prepare for it before it happens, even if the likelihood is very, very small. And if you listen to Bill Gates and you listen to Elon Musk and you listen to Sam Altman, like, the purpose is really to make AI safe. And it's not clear that we're there today. And we need some very forward-thinking people to run out and think about how we make the world safe from AI. I will contend that superintelligence would be a technology that is more sensitive, a greater state secret than nuclear technology. And these are a list of superpowers that a superintelligence might have. And instead of going and listing these, I'll talk about them in just a moment. The thing to remember is any single one of these superpowers is enough to either depose a world power or create a new world power, right? So social manipulation, hacking, technology research, economic productivity, strategizing, intelligence amplification, right? These are all superpowers that a superintelligence or even an artificial intelligence could develop. And if we don't plan for how to contain the genie before the bottle is open, it's going to be too late once the bottle is open. The other thing to think about here is that we don't have good intuition for how, this is the very last point, that anthropomorphism misleads, right? And the idea is that we're used to dealing with people. And I'm not really scared of Bill Gates because although he has lots of money, he's really not that intimidating physically, right? The thing to keep in mind with superintelligence is that they will be good at everything, and will have no intuition for how something with a 7,000 IQ that is fully well-rounded and good at everything that human beings can do will behave. Right? And this, again, goes back to the problem of value loading. How do we make sure that this uber-powerful entity or uber-capable entity is actually going to behave in a way that is conducive to human beings' survival? And if you think about what human beings have done to other species with inferior intelligence to them, it's very easy to see that a lot of scary scenarios could evolve. We don't need to worry about this yet. I think we'll all be very happy if we actually get to superintelligence. It's not clear that we can get there. That doesn't mean we shouldn't plan for it. All right. This is an interesting one. So let's talk about different types of superintelligence here. So again, this is all hummingbirds speak French. What would a United Nations be like? Let's talk about that. So the first is the idea of a speed superintelligence. How many people saw The Matrix? OK, great. So the real, I think, lasting contribution to that movie was bullet time, right? And so there's a hail of bullets coming at Neo, but he's got just tons of time, right? And the idea behind a superintelligence is that you would have a class of intelligence, and we are very, very close now. If you look at like how IBM Watson performs on text recognition, we're getting relatively close to this. A speed superintelligence in about a second would be able to read a book, or in an afternoon would be able to complete a PhD thesis. Another way to think about it, if I were to knock this presenter off the podium here, in the time before it would hit the ground, that machine would be able to read a book and order me a new presenter on Amazon before I even know that it's broken, right? So this is the idea behind a speed superintelligence. The next idea is really simple, a collective superintelligence. This, in machine learning, is something that we call an ensemble. And the idea here is we would have a bunch of narrow AIs, but we would string them together in some form of expert system or ensemble so that they collectively are good at a lot of different things. The last and most interesting one is something called a quality AI. And the observation here is that the things that make human beings extraordinarily intelligent relative to other species isn't about processing power. So if you look at a sperm whale has the largest brain on this planet. It's like a 7-kilogram brain. But we don't talk about the achievements of sperm whales when we talk about the history of civilization. Part of that's because we're just anthropocentric, we think about people. But the point here is that intelligence is not merely a function of how much raw processing power you have. What actually makes human beings intelligent and interesting in the course of evolution is the special modules that we acquired for language and for culture and for learning and communication. And so that is a difference in category. And a good way to get an intuition for this is, how do I explain this? The strongest mouse in the world is weaker than the weakest cat in the world, right? Because there's a change in category. So this is a categorical depth, or said another way, running a business and running a country are two profoundly different things, and you shouldn't confuse those two things, right? So that's the idea behind equality intelligence. We have a fundamental qualitative leap or qualitative change that leads to a different kind of intelligence. So this is the big picture of the hierarchy of artificial intelligence. That orange arrow is where we are today. And it's very, very difficult. We're wrapping up here. I've got a couple more slides. It's very, very difficult to deny that narrow artificial intelligence is extraordinarily successful. I cannot think of a Fortune 500 business that artificial intelligence won't touch. And I think does everybody remember mobile first? Right? So when the mobile phone exploded, the whole idea was like, hey, let's just design for mobile first, because that's the important emerging platform out there. Well, what Sundar Pichai of Google, the CEO of Google, is talking about now, and he's right, is AI first, right? You should, if you are working in any domain, I can't think of one which AI won't touch, you should be thinking, not over-relying on it, but you should be thinking of ways to use narrow artificial intelligence to your advantage. And what we're going to see is that companies who don't do that are going to have an extraordinarily difficult time competing. All right, so I want to add a little bit of information here for some of the practitioners in the room. So, all right, that was, okay, right, so we talked about a lot. All right, so now I want to talk about what actually makes machine learning and artificial intelligence difficult in practice, okay? So the first is this really simple idea, it's overfitting, okay? And machines are like people, they're lazy, right? If you give them a way to cheat, or if you give them a way to just memorize all the examples that they've seen, and they can run away and call that success, they will, right? So this is the idea behind overfitting, is that when we overfit on a training set, right? So artificial intelligence needs to be trained with some kind of information as a general rule. And overfitting is just essentially memorizing all of that training data, but not being able to generalize in any way. So an overfit classifier is really good on the training set, but when you show it a test set, or when you put it in the real world, it's useless, because it's just memorized the information that it has. The other problem is that now when you have exabyte scale data sets like Google does, you can find ridiculous correlations to predict anything. You can find, like, you've got so much data that you can just be like, well, you know, if we look at this person's shoe size and the day that they were, what day of the week they were born on, and what constellation was in the sky yesterday, we can predict exactly whether or not somebody's going to die of a heart attack, right? And this is very dangerous because people tend to put a lot of faith in models, and these models will be totally spurious, even though the data looks great. And the data scientists and everybody at the conference table is going to nod. You're going to use it in the real world. It's going to blow up in your face. The other thing that's hard is feature engineering, right? So we have these huge feature sets, or huge data sets, right? And then we have to pick the features that actually matter. And I'm going to talk about how we solve some of these problems in just a second. How many people have heard cursive dimensionality? Anybody? Any machine? OK, super, right? And so the idea here is that when you have a high dimensional space, you're getting more information, but the number of examples is actually shrinking. That space becomes sparse very quickly. Another problem, which my startup actually handles, is the data cleaning part. At the end, if I get a chance, I'll do a demo for you. And that just means actually getting clean, correct data into your classifiers is an extraordinarily difficult problem. Hyperparameters. So people have heard this term, hyperparameters? So many terms. Right, so the parameters, let's just take a neural network. The parameters of the neural network are like the connections and the weights in the network. The hyperparameters are things for normalization like L1, L2, momentum, weight decay. These are the parameters that you set for the model to learn. Not an easy problem at all. And just finding, this is the part that's art, right? So actually running the neural network is science, but finding the parameters that make that, you can have the right data, you can have the right algorithm. If you don't have the right hyperparameters, you're shot. And that's where this idea of auto machine learning comes in. And for the practitioners in the room and the people who want to try machine learning, I'm just going to give you a couple of quick ideas here. So if you want a turnkey machine learning system, I've been really impressed with what I've seen out of DataRobot. You literally throw labeled data at it, and it will pick the optimal classifier for you. Very impressed. If you want to explore machine learning, get started with machine learning on your own. There's two Python-based libraries. One is scikit-learn, and the other is Keras. And a general workflow that I'm seeing is people will prototype things in Python and then move to a production system like DL4J or H2O AI or TensorFlow. And we talked just a minute ago about hyperparameter tuning. There's two projects that I'm following. One is Teapot, and the other is Autosclearn. And here again, we have machines training machines to do something useful for people. And the idea here is that turn hyperparameter optimization into a machine learning problem. And this is actually Bayesian inference. It works pretty well, from what I can tell, reading the paper. Scikit feature is another one that's designed to do your feature engineering for you, right? So to extract which features are actually going to be the meaningful ones that you want to train your data on. And there's data dependencies. Let me wrap up, and I'll do a quick demo for you in just a moment. This is, how many people are people ready to go home, or should I keep talking? Be honest. OK, good. All right, sorry. So there's some really kick-ass results. I was just at Strata here, and the single most impressive piece of technology that I've seen probably in the last 5 years is something called Weld. And I'm going to talk very quickly about directed acyclic graphs. This will all make sense in just a second. Yeah. So this is called a DAG. You don't need to know what it is. What you need to know is that this is a model of computation, okay? And the model is really, really simple. And the idea is that here, at each of these nodes, at each of these circles, I'm doing computation. And at each of these arrows, I'm moving data around. And DAGs have a really nice property in that if you can express your computation as a DAG, you get parallelization and synchronization for free, right? So this is where TensorFlow actually got its name. So the flow is these arrows. And the tensors are the data that you're moving between nodes in the computation. Now, here's where things get interesting. So joint collaboration between MIT and Stanford, they built something called WELD, which is based on LLVM. And their observation was that the individual nodes run really, really fast. Like, this is Pandas, this is NumPy, this is TensorFlow, all these different libraries. They're highly optimized. They run fast. However, when you string together the whole computation, you lose all of that performance shuttling data around. Okay? So the idea behind WELD, really fascinating. So again, going back here, this is a mixed computation environment. You can have Python, you can have Java, you can have Spark, you can have C, all different types of computations. The idea behind LLVM is that you have a universal internal representation of what the executable code looks on all that platforms. And here's the punchline. WELD is able to optimize the entire computation graph. And it does so lazily. It doesn't actually do any computation until somebody actually materializes the result. Now, here's the cool part. These speedups are ridiculous, ridiculous. So if you look lower right. Let's just start there. 2 orders of magnitude speed up on Pandas and NumPy relative to WELD. That's unheard of. You're going 100 times faster just by optimizing the computation. Same thing, 10x speed up. So TensorFlow is written by the best programmers in the world that work for Google. You would think it would be fully optimized. You would be wrong. If you throw a machine optimizer at that, it can give you enormous, enormous speed ups. And the trick that they played in WELD is that you don't have to, there's no source code changes. It's API identical to the original. You just pop in a few WELD routines. Does anybody use Pandas in this room? OK, great. So they made a version of Pandas called Grizzly, which is API identical. It's just 10 times faster at the critical operations. A lot of good things to come. It's also implemented in Rust. So looking out into the future, I expect great things from Rust, LLVM, and WELD. WELD, W-E-L-D. Yeah. Uh-huh. It's a performance optimizer. You can think of it as a graph compiler. In addition to. Yeah. Yeah, and it's up to you how much you want to use it. But again, the idea is you have to change the libraries. You don't change your source code. It's super cutting edge stuff. It's fascinating. All right, so let's see if we can wrap up here. So we started out with a really simple definition of artificial intelligence. That's machines acting like human beings. We talked about some of the sub-disciplines in AI. We established, I hope convincingly, that you can never have an objective artificial intelligence or an objective human intelligence for that matter. We established why this is important, because huge parts of the global economy and our personal attention economy are going into AI. And we mentioned the fact that this is a great way for us to know ourselves, right? We're spending hours a day training algorithms on Facebook who the important people in our life are. Is it right? Is it actually getting that right? We talked about the advent of narrow AI. This is where we're actually doing really well. We talked about some of the things that make general AI difficult. And we talked about this general hierarchy and what the advent of superintelligence might mean for humanity as a whole. We looked at evolution as computation. And we talked about the things that were hard in practice. All right. What is the conclusion? So I guess the one thing to walk away with is that we tend to think of robots and machines as being perfect in ways that people are not. And if you look at recent history, you look at blow-ups, you look at the 2000, and without making any value adjustments, the 2016 election, all the models were wrong, every single one. But there were very few people who actually predicted that accurately. You look at the Fukushima disaster. It was out of model. Well, I think it was built for a Richter scale 8 earthquake, and then they got a 9, right? And you hear experts apologizing over and over again, we never could have predicted this. Well, the thing to predict is that we're shit at predicting. That's the thing that everybody should get really clear about. And other examples, long-term capital management, the 2008 financial crisis. Oh, we never expected this. This wasn't in our models. And a human being with a model is a very dangerous entity. And if we treat AIs as oracles, they will blow up. And we will blow up spectacularly because we will put that AI in front and say, oh, I have this amazing, this spectacular model with 99% accuracy, and we'll bet the farm on it and we'll blow up. Because that AI always has blind spots. We also talked about the machine as a mirror. That was the whole point behind inceptionism, is that you can feed a machine unbiased information and peer into what its biases are. And then we talked about intelligence application, which is human beings and machines working together. I hope in all of this that we don't lose the quest to just increase human intelligence. That's the simplest and easiest thing that we can do. You give kids in South America or any developing nation running water, and the average IQ jumps by 10 points. Right? There's a lot of simple things we can do. It's not always involving technology. Question?
Yeah, so if, for example, a model has a really high accuracy, more than 99%, won't you necessarily be more entitled to rely on that rather than anything else? I mean, for any specific reason. For example, if you're modeling for your financial outcome or you're trying to model for your next
Yeah.
something has a 99% accuracy, why would you not move forward with that? Or why would you still be so skeptical about it?
Yeah, so you just explained why high accuracy is so terrifyingly dangerous, is because people will put faith in it. And I hate to recommend a book as the answer to the question, but this is called a black swan. So a black swan is something which wasn't in any of our models, nobody predicted, should be impossible, but then actually happens. And my submission to you is that 99% accurate model will be swimmingly fantastic and amazing, and it will have 10 or 20 years of great performance, and then the entire world will melt down because of it. And that's exactly what we saw in the financial crisis. Like, oh, we have these Gaussian models. This is what happened when long-term capital management blew up. They're like, look, they literally said, this is a 6 sigma event. It's 6 standard deviations away from the mean. It's impossible. It can never happen again. 3 Nobel Prize winners all said this. This can never happen again. It's perfect. And they doubled down. And it happened again. And they said the same thing. They said it can't happen again. And then they blew up again, and the Federal Reserve had to bail them out. That's the answer to your question. It's perfect until it's not. All right, so bibliography. I'll make sure that Chris has these slides, so they're on the Galvanize site. I would still like to do a demo, but I want to take more questions. That's everything I wanted to talk about. I didn't really go into details everywhere, but I really want to hear from you and hear what I can sharpen up for you or what questions you have.
Before we do questions, I just really want to stand up and thank Aneesh for his time.
Thank you.
Just because I love hearing Aneesh talk. It's always inspiring and raw at the same time because he really does say what he's thinking. So I love that. So I just want to take some time and thank Aneesh for presenting before we do the Q&A.
Yeah.
So, you talk about wealth as just-in-time compilation. Is that how it's accomplishing this with us?
Yeah. So, right. This is actually a great question, and it's an excuse to talk about more interesting things. I'm going to back up. Please close your eyes if you get motion sick, because we're going to. Oh, wow. OK. So the question was how weld works, and the idea. Yeah, we're there. Yay. OK. So the idea. OK. So first, a little bit about LLVM. So the way LLVM works is actually the way the human brain works, and that's that it has a front end which can take any type of language as input. You can have front end for Python, you can have front end for Java, like pick your language, pick your poison. It then has an internal representation, and all LLVM is good at is optimizing that internal representation. So it takes an IR, an internal representation, it presents an optimized IR, and that optimized IR can then be emitted with a backend to any platform that you want to emit it on. So there are 3 things that make weld fast. Okay? So the first thing is the performance critical routines in any given library are swapped out with highly optimized weld routines. That's the first thing. Okay? The second thing is that now, instead of trying to optimize a single computation node, you're optimizing the entire flow of the computation. So this is global optimization across languages, and that's why it's amazing. Right? And the third thing is just the laziness. Right? It's like, you know, you don't actually have to compute. Here's a great example. Like, let's say there's 1 trillion rows in your database at A, but you only need 2 rows at I. You can be really, 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 really lazy and wait and not do a lot of work. Does that answer your question? It's mind-blowingly good. I couldn't believe it. I'm waiting to find out what's wrong with it because it's amazing. Yeah, LLVM, let's think about this for a second. It definitely runs on Macs. I'm pretty sure you can run LLVM almost anywhere.
So, is Google going to get its hands on it?
I mean, it's open source. They have it. Yeah, but it's all open. It's actually on GitHub. The truth of the matter is, I do believe in these numbers. They're really impressive, but actually integrating this in practice is going to take a long time. It's going to be hard.
So it's open source.
Yeah.
And how many people know how to apply it?
That's a good question. The mailing list has very low traffic and only a few people on it, but just came out. It came out. What's that? Yeah, but I mean that's how things are, right? It just came out like 2 weeks ago. But after, I think a lot of people are going to look at it. But that's just what I think.
That's probably not hardware accelerated TensorFlow, like somebody just mentioned that, because Google has silicon for hardware accelerated.
I think this is with GPU optimization and everything. I think this is fully optimized TensorFlow, and the reason is that an optimizing compiler can always do one better for you. And actually, GPUs should only make Weld better, and that's one.
Google has like hardware; they have like their own silicon.
Yeah.
For Tensor, it's not non-GPU. That's like silicon.
Yeah, great. So that's one of the huge things that Weld does is vectorization for specific architectures, loop fusion, loop tiling. There's all these. Yes. So no, hardware will make Weld better. Will make Weld better. I just want to show you a demo of what we're working on at Quilt real quick. Any other questions? Yeah. I think that'll be the last thing for AIs to accomplish. And because once it happens, look, this is why the superintelligence takeoff is so startling, is that if you had a general AI, what is the first thing you would ask it to do? Make a smarter AI. Right? You can actually issue that instruction. And code writing code is right in that bootstrapping kind of wheelhouse. So I think code writing code is really, really difficult. And I think it stretches the boundaries. This is the strangest thing. I think being able to write code is one of the things that actually makes us human. And I think it's going to be really, really difficult to get machines to do it. Once they can do it, it's checkmate. I think we're all out of a job. I don't know what's going to happen after that. Yeah.
A basic question. Those images you showed in the beginning, are those examples of overfitting models?
The images I showed at the beginning.
Beautiful images you showed.
Yes.
That were turning clouds into a beautiful. Is that an example of overfitting?
No. That is hallucination. So I guess no, it's not overfitting because it's not that. OK, the reason it's not overfitting is that classifier is very successful in practice. And it's very successful on unseen training examples. What that is just the bias of the machine coming out, right? It's just you're looking at the hypothesis that it's formed. And what we're seeing is that every hypothesis is imperfect. Yeah. So I mentioned earlier data movement and data integration. And I think there were a fair number of hands that went up. Oh, can I get on? What's the Wi-Fi password? Oh, don't need one. OK. So I'm really excited about this because one of the things that we want to achieve at Quilt, it's a 3-person startup, it happens to be my company, is to make it really, really easy for data scientists to, wow, how did that happen? Oh, does that matter? Can I kill this? Let's just play nice. This is my email address, by the way. I hope you'll all stay in touch. I feel that, OK, great. Access the web. Thank you, computer. OK, right. So what we realized is that data scientists were spending a lot of time, 80% of their time, finding, cleaning, and organizing data. So what would happen if we actually made data sets installable the same way that GitHub packages are installable or pip packages are installable? And the high-level bit is that it's really easy to install, compile, and version software, but we don't do that yet with data. So here's how Quilt works. I'll just show you in a nutshell. So the idea is that when you have a data package, you can pull that down from the cloud, and If you're familiar with Docker, we learned this trick from Docker. All the packages, the data packages, are namespaced. So I can do quilt install acarv / let's try this nyc jobs. Okay, and that will go out to the cloud and actually get the latest version of this data package for me, right? And now if I do a quilt log, well, let's try that again. If I do a quilt log acarv / nyc jobs, you'll see something that you're very familiar. What did I do? Yeah, you'll see something that as a GitHub user you'll be very familiar with, and that is that each of the data packages are uniquely hashed. Right? So the first thing you need if you want to be able to reproduce your analysis is you need to be able to travel time. So we're doing this with data. We're actually versioning the data. And here's the cool part. It's a very quick demo. So if I fire up something like Python, now I can import data the same way that I import code. Right? So we're used to like going on pip and finding the building blocks that we need. But where do people get the data building blocks that we need? And that's what we're building Quilt for. So I'm going to import data and meta. You'll see what that is in just a second. Did we fix this bug? Let's try this. OK, so. No, Pickle is extremely slow. And we're getting off Pickle onto Parquet. But give me 1 second. I'm just going to build this package again. OK, great. So the same way that you compile source code to get high performance from a memory standpoint and from a performance standpoint, you can compile your data. And what we're doing here is, so if I'm going to do a quilt build. Let's build this data set here. So I'm going to do a quilt build this package, which is acarv / nyc jobs. And I'm going to give it this build.yaml file. And what this is going to do, oh, help me, God. OK, yeah, there we go. This is going to do is this is going to provide a memory mapped IO optimized format for my data. OK, so you'll see that it actually took a minute to index and compile the data. And what this does is now, instead of parsing when I load the data, it should work just fine when I actually load the data now. Instead of parsing when I load the data, just copying binary blocks off of disk and into memory. It works much, much, much faster. So let's see if we can try this one more time. So now, from this package namespace here, I'm going to pull in a data package. So I'm going to import the data and the metadata. Let's see what we get here. Yay. OK, good. And wait for it. OK, there we go. And then you've got data, right? And so this is the idea, is that the same way that on GitHub, on NPM, you have these great software building blocks, we want to make it really, really easy for people to find optimized data, inject that into their machine learning models, build data science models out of this. And it's really, really easy to glom onto how packages actually work, because each of the packages, once it's public, actually has a landing page like this. So you can document your data. People can see hashes and who published your data. If you're working in data science or machine learning, please come see me. I'll give you my card. I would love to partner with you as you build up Quilt. Yes?
Maybe it's a dumb question. What do you mean by optimized data?
Right. OK, so if you look at the slowest thing in computation, which is also true for Weld, is I/O, always. There's one thing slower than I/O, and that's doing parsing on top of I/O. So if I have a directory, if I have 100 CSV files, 100 Excel files, and I try and load those into memory using something called like pandas, right? It's going to go through and parse each of those files. OK. However, if I actually compile that data and convert it to binary format, I don't have to parse anything. I literally take blocks off of disk and I load them directly into memory. And that's somewhere between 5 and 20 times faster. So optimizing the data is putting it into a format that the machine can read more directly. And there's all kinds of tricks you can play, like byte reordering, columnar data. That's a whole interesting. And that's what the Quilt compiler is all about, is making it so your data loads really fast.
So that's what your software does? It optimizes data?
That's right. Any data.
Pull the data and it optimizes it. So how does the algorithm know how to read your optimized formatted data?
Oh, because the file formats are already really well established. So most of the data science software out there knows how to read Parquet, knows how to read Feather, knows how to read HDF5. That work's all been done. The real value, though, is having this centralized hub of data and then being able to go find building blocks and just install them and not worry about.
LTK has like its index of like data, but it's sort of like like in LTK when you grab like tokenizer or
Right.
something like that, it has its own thing for doing that. Then it's just like LTK specific.
Yep.
And so there's like this kind of provides like a public repository for this type of thing for all types of data.
Exactly.
People use it for their formats of data as well.
Exactly. Exactly. And the most interesting point there is not just the performance optimizations we're doing for the computer. We are freeing up people to do more interesting things. You should not, if you want to learn machine learning, you shouldn't spend your Saturday like, oh my God, what training data? Where do I find this training data? Oh, it's too big for my computer. Like, you should be able to forget about all that. And that's the big idea. It works on Python today. We're working on R and Spark. And it's basically data virtualization, right? You can get the same data wherever you are. Anyway, enough about Quilt. So again, if you're working in data science, please come see me. I would love to talk to you. If you're just working with Python or machine learning, I would love to talk to you. And is there anything else, any other questions I can answer while we wrap up?
Can you bring that bibliography up one more time?
Sorry, the presentation?
Yes.
OK, yeah. Go.
The bibliography part of the presentation.
Sorry, I'm sorry. Oh, the bibliography. Yeah, sure. It's the there we go. Da-da-da. There it is. Yeah, sure. Chris, I'm sure there's a site online. I don't know where you want to make the.
We can put it up on both meetings.
OK, super. This will be on the internet, or you can take a picture of it, as I think many people are doing now. Yeah.
So I first learned about neural networks like 13 years ago, and it was like, oh, cool, AI. And then, it was a long time, and all of a sudden, neural networks, they're everywhere. What changed? Like, why now? Why not? I mean, it's not like no one knew what a neural network was 20 years ago.
Right. OK. So the question was, I think, please tell me if I got this right, is that AI has been around for a long time, and frankly, the history of AI is the history of under-delivering. And then all of a sudden, out of nowhere, neural networks became really, really important. The answer is first is several-fold. So first is the maturity of the discipline. It's just people working with things. The fact of the matter is that progress takes time. When it happens, it's very sudden, but there are a lot of small steps that people need to take in order to make that breakthrough possible. That's the first thing. So it's just working with the technology. The second thing is we've enjoyed 10 or 20 or 30 years of Moore's Law, right? And that has a tremendous effect. I'm not one of those people who actually believes, I think that GPUs are important to deep learning, and you can see it in the NVIDIA stock price, but deep learning is not, it's about hardware power, it's not about specific types of hardware. So it's a combination of practice, right? People working in their discipline, developing it theoretically and practically, having lots of really, really good data, and having fast computers. And it's amazing. And here's the human part, trying weird things. Because remember, it was a law that you only needed 2 layers in a neural network. I remember being taught this. I remember it so clearly. And I was so proud of myself that I'd memorized the mathematics and be like, you can approximate any bounded continuous function with a 2-layer neural network. Horse fiddle. I mean, you can, but it doesn't work well in practice, right? So does that answer your question? OK, great. Well, I'm not going to keep you much longer. Please come up and talk to me at the end. And my email address, if you'd like to stay in touch, is right here. So it's been a pleasure, and I hope to see you guys again. Thank you.